Okay, so our last for the last talk of this of today, I want to introduce Dave Marker, who will speak on some reflections on Udi's work, and I would like to personally thank Dave for agreeing to give this talk on a fairly short notice. I mean, we've asked him. We thought that the conference in honor of Udi's was a good idea, and the maturity of the subject were a good point to maybe have some sort of historic perspective on the field. That is something that also Anand mentioned in his talk, that this may be time to start thinking in that direction. And this will be Dave's rendering of our request. So thank you so much for agreeing to do this, and the stage is yours.
Thank you, Asaf. I'm really pleased to have the opportunity to speak here at this workshop in honor of Udi's 60th birthday. Though, as many other speakers have said, it's bittersweet that we're not able to gather together for this. It was a great pleasure to me to be able to spend a large part of the fall at Fields and actually interact with a number of you in person. So, as Asaf said, I was asked by the organizers to give some overall perspective on Udi's work. I mean, this seemed to me like an impossibly daunting task, but Elizabeth assured me it would be fine if I were to focus on some of my personal favorites, which is what I'm going to do. While I may not be the most natural candidate for this lecture, I do have the perspective, I think, of knowing Udi longer than almost anyone here. We first met in fall of 1983 when I was a postdoc at Berkeley, and Udi was a graduate student of Leo Harrington. Chris Laskowski, if he's here, might be the only person who has known Udi longer. I really think it's difficult to overstate Udi's influence on our subject. As Tom so eloquently said in his opening remarks, Udi fundamentally changed the way that model theory interacts with classical mathematics. Much has been made of the real or imagined divisions between pure and applied model theory. But if you look back at the landscape and what it was like in the early 80s, this is perhaps a reasonable way to describe the situation. Let me give an oversimplified overview. On the pure side, there was the work of Jouanolou developing a general theory of independence, extending the work of Morley, but a lot of this was focused on general structure theorems, where to many of us who weren't actively involved in this, the applications and motivations seemed to be primarily in model counting theorems. Although in retrospect, we see that there's a lot more that even those of us who were skeptical at the time, see there's a lot more there. Also, Zilber was beginning the development of geometric stability theory, focusing on the combinatorial geometry of independence. On the other side, there was sort of the Robinson tradition, where one applied basically basic model theoretic techniques, 1950s model theoretic ideas in algebraic settings. Now, this had great successes, say, in the work of Ax and Kochan and Yershoff, and in McIntyre's theorem on a quantifier elimination for the p-adics. And there was also a body of work where one took stability theoretic assumptions and looked at algebra under those conditions. I'm thinking of, say, the work of Angus on omega stable fields, and the work of Cherlin on, and Zilber as well, and others on groups of finite Morley rank. But high-powered pure model theory seemed not so connected to mainstream mathematics, maybe with the notable exception of the work of Lenore Blum on differential fields. So this is when Udi enters, and sort of standing on the shoulders of giants, I think of Udi's work as leading to the great synthesis. On the one hand, we realize now that interesting model theoretic phenomena was often the avatar of algebraic structure. I'm thinking here, say, of Udi's work that non-trivial, locally modular, strongly minimal sets are naturally intertwined with groups. And again, some of these ideas were already in the air with the work of Zilber. But this also comes up in things where you would not expect algebra at all, such as the Hrushovski-Laskovsky analysis of spectrum functions. On the other hand, Udi's work on Mardell-Lang, in this work, core model theoretic ideas have surprising algebraic and number theoretic consequences. And moreover, while Mardell-Lang needed a few new ideas on finite Morley rank groups, the proof seemed to grow almost organically out of our current understanding of geometric stability at the time. And this theme has continued in, over several decades in Udi's later work, say on algebraically closed valued fields and on approximate subgroups. Okay, Udi's always been a wonderful person to discuss mathematics with. In addition to his deep insights and broad perspective, he's been particularly generous with ideas. He's been an excellent mentor and collaborator for many of the young people in our subject and many of the older ones as well. Now, an experience that many of us have had is working for a long time on a particular problem and then having a short discussion with Udi that simplifies and clarifies everything. And I want to begin today for the first part of my talk. I'm giving, almost complete details on an example of a result of Udi's where this happened to me. Okay. So this is work on strongly minimal expansions of C. At the time, and this was in the, again, mid-80s, I think, still, maybe late 80s, Udi and I were both thinking about Zilber's conjectures on strongly minimal sets. And one of the conjectures was that one could not add significant structure to an algebraically closed field and keep a strongly minimal set. And Udi proved the following pretty result. Okay, suppose, and I've stated this all for the complex numbers because that's where my work came in, but everything I'm doing here would work in an arbitrary algebraically closed field. Suppose I have a non-constructible subset of n space, and I look at the structure obtained by adding a predicate for this x, and that this new structure, suppose it's strongly minimal. Then in fact, while I may have added a subset in n space, I've also added a new function from C to C that's definable but not constructible. So this tells me that I've really changed the notion. I have to change the notion of definable closure to get new strongly minimal sets. And it's also the case that for any irreducible algebraic curve, the intersection of C with the graph of F is going to be finite. And this tells me that I also have to have changed the algebraic closure relation. This result has a very elegant and short proof, so I'm going to actually go through it. So first, let's look at n. Let's take n to be minimal, such that there's a new definable set in n space. Okay. Then for any a and c, I can look at the fiber above a, and these are subsets of n-1 space, so these sets are constructible. So they're going to be defined by some formula in the field, which depends on A, and then there's some parameters that define it. Well, by saturation, we don't need a different formula for each A. Finally, many formulas would suffice, and then by usual tricks, we can go from having finally many formulas to one formula. So for each A, there's going to be some parameters B, such that this set phi xb will define the fiber above A. Okay, so as usual, we now want to look at the equivalence relation that says that two parameters define the same set. Okay. And we use elimination of imaginaries to get a function from Cm to some higher dimensional space or some dimensional space Cl, such that so C and D define the same set using phi if and only if G of C is G of D. And this argument all takes place just in the algebraically closed field language, so these things are purely constructible. So now in my new structure M, I can define a function from C to CL, which basically takes me from A to a canonical parameter for XA. So f of A is boldface B if and only if there's some C such that using C, I define XA and G of C as B. Okay. Of course, given F, I can reconstruct X. AX is an X if and only if there's a C, so G of C is F of A and phi of XC. So this function F has to be a new function. So this tells me I've added a new function from C to the L. And by taking some coordinate function of F, that's going to be a new function just from the field to itself. Okay, so if I've had, so this argument is if I have any, if I can expand the field in any way, in any non-constructible way that keeps it strongly minimal, I've actually added a new function from the field to itself. Okay, so now we want to do the second part. So suppose C is some irreducible curve, and the graph of F, and the graph of F has infinite intersection with C. I mean, since it's non-constructible, it also, the complement will also be infinite. And now there's a nice geometric argument to argue this is impossible. Okay, so first, without a loss of generality, okay, I've defined C as an affine curve, but it may well just be a smooth projective curve anywhere. And I've got some definable set in this curve that's infinite and co-infinite. Now, if the curve had genus 0 to begin with, then it's birationally equivalent with the field. And pulling back H inverse, that's going to be some infinite co-infinite set, and I get a contradiction. Okay, so suppose it has genus 1, then it's an elliptic curve, which is in particular a divisible abelian group. Now I want to look at what the generic types are of C in my new structure M. So I've got this infinite co-infinite predicate X, so they're going to be generic types that are in X and generic types that are not in X. I mean, C is still going to have Morley rank 1, and X and the complement are infinite co-infinite sets. So that tells me that C has Morley degree at least 2, and then standard omega stable group theory tells me that that C is not a connected group. So the connected component is going to be some proper definable subgroup of finite index. But as I said at the beginning, I'm in a divisible group. So there are no finite index subgroups, definable or not. So this is impossible. Okay. And if G is 2 or higher, a similar argument works using the embedding into the Jacobians. I won't go through the complete details here, but basically, anytime I have a curve of genus, let me say at least 2, I can embed it into an abelian variety where the dimension of the variety is the genus of the curve. And if I take G independent generics of X and Y independent generics in the complement of X, and look at the sums of their images, those are going to give me distinct generic points in the Jacobian. And once again, that tells me the Jacobian has Morley degree at least 2. So it has proper finite index definable subgroups, which contradicts the divisibility of the group. So I mean, this is I've now given you the entire proof of Udi's result. I think this appears in I believe at the beginning of his paper, Constructing Fusions. Okay. So what was I thinking about at the time? I was also thinking about Zilber's conjecture, but in a very concrete way. What I wanted to show was that I couldn't build a strongly minimal expansion of the complex numbers by taking real algebraic structure. So what I was doing was looking at subsets of R2n, viewing them in a natural way as a subset of Cn, And the result I showed was that if I take X that's semi-algebraic, so definable in the real field, and then either the X hat I built is constructible, or if it's not constructible, I can, when I add this predicate X hat, I can define the reals. Okay. So the first big step in the proof, which Udi's result doesn't help me with, is if I start with a subset of R squared, then I'm defining a subset of C. And if this is non-constructible, we can define the reals. So that's the first result I had shown. And I think in this case, it wasn't even important that X was semi-algebraic. O-minimal was good enough. And then what I did was a quite complicated induction using Bertini's theorem and using semi-algebraicity heavily to show that if I had a constructible set anywhere, I would get one in, I would get one on the line. But let's instead use Udi's result. Okay, so by O-minimality, I have uniform bounding. So since I have no infinite or co-infinite subsets of the reals, that'll still be true in any elementary extension. So not only is this minimal, it's strongly minimal. So I have an example of a strongly minimal expansion of the field, complex field. So by Udi's result, I know that there's a non-constructible definable function. So I have f, a non-constructible function that's definable here. Of course, it's looking at the coordinates, it's a semi-algebraic function. And now I really want to look at the coordinates. So x0 and x1 are both graphs of real functions. What x0 does is it takes me from A to the real part of f of A. And x1 takes me from a real A to the imaginary part of f of A. And again, since these things are all semi-algebraic, I can do this in the reals. But these are now graphs of semi-algebraic functions on the reals. So I can find polynomials P0 and P1 such that these graphs are contained in the curve Pi xy equals 0. And this is just a real algebraic curve. So this sort of these real algebraic curves control the functions which are giving the real and the imaginary parts of f for real arguments. But then for any x in R, xf of x is in this set. The set of xy is such that there's z1 and z0 and z1, such that p0 vanishes at x and z0, p1 vanishes at x and z1, and y is z0 plus z1 of I. Now, it may not be clear immediately what this is doing at complex numbers, but if I start with a real number, then the way I've constructed this, this is going to contain, this set contains the graph of f at least restricted to the real numbers. Now, the set I defined here is a one-dimensional constructible set. It follows that except for a finite set, the graph of f is going to be contained in some irreducible component of V. And now this completely contradicts Udi's result. Okay. So this was actually about a 20-minute conversation I had with Udi at a meeting in Maryland in the maybe late 80s. And somehow at this point, I'd sort of understood that I could take half my argument and replace it by Udi's pretty result and this little argument about semi-algebraicity of functions. I should say that although I use semi-algebraicity heavily, using Udi's results, this is the only place where semi-algebraic comes in as opposed to O-minimal. It was left at that time as an open question whether this would also be true if I looked at O-minimal, just at O-minimal. And this was shown later by Kobe and Sergey. Okay, so that's the first part. So the second part, I want to concentrate on, oh wait, sorry, I should say this. Of course, the punchline was, and this was done not long afterwards, is Udi's great result that there are these really weird fields out there for nice model theory. There are strongly minimal fields where I have two field structures on them, one an algebraically closed field of characteristic 0, and the other an algebraically closed field of characteristic p. This is proved by what's now called a Hrushovski fusion construction. And the key difficulty, and this is one reason why I, at one point, before this was proved, lamented this would probably never be done, is, I mean, you have to, let's say in this particular case, you have all these, I have curves of degree, I have families of curves with respect to one field and families of curves with respect to another. By strong minimality, there have to be uniform bounds on the cardinalities with their intersection. So what you need to do here is prove some kind of wild generalization of Bezout's theorem, bounding numbers of intersections of things in different families, where these are coming from wildly different structures. This seemed like a very difficult idea, but ultimately, when Udi's proof came out, I mean, this was sort of the key to how you control things, is that you build these up and you force along the way, you force intersections to be the sizes you want as you go along. Okay, so that's the first part. The second part, I'm going to talk about my favorite subject, which is, and discuss it. Also, I think I can almost in 20 minutes or so describe almost all of Udi's work on differentially closed fields. There are a handful of papers, or preprints, all of which are somehow among the most seminal and important works in the subject. The one I want to start with is the famous Hrushovski-Sokolovich preprint, which I think unfortunately has never been published, although all of the results in this now appear elsewhere and somewhere scattered in the literature. I want to work in a differentially closed field K. I always use math bold to be just some sort of universal one. The constant field is just the elements which have derivation 0. And this paper gives a remarkable insight into what the strongly minimal sets are, at least the non-trivial ones. So first we want to look at the first result is that if I take any strongly minimal set in a differentially closed field, then perhaps I have to throw away finitely many points. But if I look at X with the relative Colchin topology on all of the powers of X, then I get a Zariski geometry. So using the fundamental theorem of Zariski geometries, fundamental theorem of Zariski geometries will tell me that anytime I have a non-locally modular Zariski geometry, it's non-orthogonal to a infinite definable field. Now, we knew beforehand, I think through works of Manin and Sokolovich, based on works of Phyllis Cassidy on differential algebraic groups, that the only finite rank fields in a differentially closed field is the constant field. So what these two results taken together tell us is that if we're trying to understand the non-locally modular strongly minimal sets in a differentially closed field, there's essentially only one, the constant field. So this is an instance of the Zilber program in this setting. The corollary was later given a more elementary proof that didn't involve Zariski geometries using the canonical base property for differential finite rank sets of differential fields that Manin talked about a couple of days ago. Okay, so next question is, what about non-trivial locally modular strongly minimal sets? And here, once again, Hrushovski and Sokolovich gave a complete classification, which is a remarkable result. So we begin by relying on some earlier work of Manin and Ali Bouim, So let A be a simple abelian variety. So this means no proper infinite abelian subvarieties. That's not isomorphic to a variety defined over the constant field. So you needed some parameters from the differential field to define it. Then I can find a non-trivial algebraic group, differential algebraic group homomorphism from A to the linear group, the vector space K to the D. Now, of course, in the algebraic geometric category, this is impossible. Any map from an abelian variety, any algebraic map from an abelian variety to a vector group is necessarily constant. But here, this is possible. Moreover, if you look at the kernel of this homomorphism, it's the minimal, I say but it should be the minimal infinite differential algebraic subgroup of A, which necessarily is the Colchin, well, in the simple case, is necessarily the Colchin closure of the torsion points. So I think much of what I said up so far is in Boehm, but the model theoretic consequence, the model theoretic result here is that these kernels you get are strongly minimal and are locally modular. If I started with an abelian variety that was defined over the constants, we know we have maps mu like this that are logarithmic derivative maps, but in those cases, the kernels we get will be just sort of the constant points of A. And so clearly non-orthogonal to the constants. But this will give us, so this gives us the first examples we knew of locally modular strong minimal sets in differentially closed fields. Moreover, when we have strong minimal sets, we want to try and understand them up to non-orthogonality. And here there's a nice characterization of when these are non-orthogonal, that if A and B are abelian varieties that are not isomorphic to abelian varieties defined over the constants, so that the A sharp and B sharp are locally modular, then they're non-orthogonal. You can detect that again just from the algebraic geometry, that this is true if and only if A and B are isogynous abelian varieties, which means that there's an algebraic, so a homomorphism in the algebraic category from A to B, which has finite kernel. So you have this intimate algebraic relationship between A and B that creates the model theoretic algebraic relation between A sharp and B sharp. Finally, this gives me a complete classification of the non-trivial strongly minimal sets. If I take any non-trivial locally modular strongly minimal set that's defined in K, it's going to be non-orthogonal to one of these Manin kernels. And a key step here is, again, one of the crucial contributions of Hrushovski to the subject, and I think part of his thesis. It's a result that in a non-trivial locally modular strongly minimal set, you always find some group somewhere. But these are always non-orthogonal to some kind of strongly minimal group. And then in our setting, we could analyze what the strongly minimal groups are and argue that they either have to be related to the constants or have to be one of these Manin kernels. Of course, this leaves open the question of what happens in the trivial case. And, there's been a great deal of work on that in the last 30 years by a number of people. In particular, work of like Pillay and Jouanolou on Pon-Levé equations, work of Freytag on many things. So this is the work of Scanlon and Freytag on the differential equation satisfied by the J function. All fit into this, still trying to understand what happens in the trivial case. And I'll say a little bit more about the trivial case when I talk about Udi's next results. But sort of the punchline of this paper was what I'm calling Vaught's conjecture for differentially closed fields. Of course, that's not strictly speaking true. I mean, Shaw in the early 80s had proved that any omega stable theory satisfies Vaught's conjecture. So there was an embarrassing 10-year period where we knew that differentially closed fields had either continuum many or Aleph zero non-isomorphic models, but didn't know which the answer was. And a corollary to this result proved in this paper is that there are actually continuum many non-isomorphic countable models. And the idea is that these non-trivial locally modular strong middle sets, the Manin kernels, you're allowed to assign different finite dimensions to them. And there are many of them. And you can use these now to show that you have Shalazian IDOP, or just to explicitly code isomorphism types of graphs into isomorphism types of differentially closed fields. So we end up getting lots of models. Of course, while I said this was the punchline of the paper, it really was just the starting point for the importance of this paper, and that the real importance came shortly afterwards in Udi's paper on the Mardell-Lang conjecture. So in the characteristic zero case of the function field Mardell-Lang, these results play an essential role. And I'm not going to talk about this in any detail at all, but I just want to go through sort of the simplest way you can see this coming up, just from what I've told you so far. So let's let little k be an algebraically closed field and big K a finally generated extension. And let A be a simple abelian variety over big K that's not isomorphic to an abelian variety over little k. And let V be a proper subvariety of A. Then my claim is that V contains only finitely many torsion points of A. Now the fundamental step here, and this was also a fundamental step in Boehm's work, is to pass from this algebraic setting to a differential setting. So it's easy using Chevalet's work, extension theorem, to build a derivation on K, big K, that has constants little k. And then I can pass to the differential closure of big K, and we know that that adds no new constants. So I've built this bigger field, L, over which everything's defined. The constant field is little k. And now what I want to do is I want to construct in L the Manin kernel of A. That's going to be some definable, strongly minimal subgroup of A, and it contains all of the torsion. I mean, you can see that from the argument, the torsion has to be in the kernel of the Manin homomorphism because I've killed the torsion when I've gone into the vector group KD. Okay, so by strong minimality, A sharp intersect V has to be finite. Otherwise, V would be you could show that V is a coset of a proper abelian subvariety, and we're assuming there is no proper abelian subvarieties. Okay, to get from here, this is sort of the basic core of why differential algebra has something to say about this. To get the full Mardell-Lang, even in characteristic zero, you need things like the Hrushovski-Play result on one definable sets in one base groups, which a few weeks ago I claimed was one of my favorite theorems of Manin's. And you do a little bit new structure work on structure of finite morally ranked groups. And this leads then to Hrushovski's proof in characteristic zero. And this gives a template for what you're going to do in characteristic P, although in characteristic P has some very different ingredients in the proof, but it sort of follows the same general outline. Although we're working with infinitely definable things instead of definable things. Okay. The second paper of Udi is in differential algebra, and I say paper, but this is really just unpublished notes. And when I pulled them up yesterday, I see they're even untitled unpublished notes. But it has this very beautiful theorem in it that's been used a number of places. So suppose I have a strongly minimal set that has transcendence degree 1. Let me just, and by transcendence degree 1, I explained below that means if x is defined over k and little x is a generic point of x over k, then the differential field I get generated by x over k will be a transcendence degree 1 field. An easy way for this to happen is if I have just a first order differential equation. So f could be any polynomial here, any polynomial over k. Or I could look at D varieties. So where the set is a strongly minimal subset of a differential, of an algebraic curve, and this curve, and the function field of the curve is the differential function field of the variety. Anyways, so that's what I mean by transcendence degree 1. So what he proves is that in the transcendence degree 1 case, of course, it's possible that you could be non-orthogonal to the constants. That easily happens. But it's also possible that, but if not, then what you have is ellipse-zero categorical. Indeed, after you throw out finally many points, this set is just a finite cover of a set that has absolutely no structure whatsoever. I mean, there'd been a conjecture by, which I think Lescar attributed to Poisson and Poisson attributed to Lescar, that any trivial strongly minimal set is ellipse-zero categorical. This was sort of evidence toward proving that. That was later refuted in the work of Freytag and Scanlon. The key to this theorem is the following theorem. The key to the first proof is this following theorem, which shows you again that differential algebraic geometry is very different, strange world compared to algebraic geometry. I mean, suppose I have a Colton closed set of transcendence degree D that's defined over the constant field. Then there are two possibilities. Either there are only finitely many D-1 transcendence degree subvarieties, differential subvarieties of V defined over C, or I can find a non-trivial map from V to C. And then in the latter case, the inverse image of every point will be a transcendence degree D-1 subvariety of V. So this says that either you have, so you can't have large subvarieties of V defined over the constants just for arbitrary reasons. If you have them, then you have this whole family of them. And Play and I used this at one point to argue that in certain cases you had then rank 2, morally rank 2, and U rank 2 had to be the same. Let's say these. Well, something like that. But that may not be exact. I think that's not exactly right. His proof, he worked by using the extension of a theorem in algebraic geometry of Jouanolou on Pfaffian forms. As I said, this paper was never published, although in the last few years, Freytag and Musa have extended this result, both to the partial differential setting and in looking at things that aren't defined over the constants. So this results now do appear in print. The third paper I'll mention briefly is a paper with Masanori Itai on model complete differential fields. The theorem there is so an anti-McIntyre-Van den Dries-McKenna theorem that there was a conjecture going into this that if I looked at a differential field that was omega stable, it would necessarily be differentially closed. This shows this is as wrong as possible. They show that there are continuum many theories of differential fields that are omega stable with quantifier elimination. Omega stability is a red herring here, because once you eliminate quantifiers, that tells me that types are the same as differential ideals, and the basis theorem for differential algebra tells me they're only the differential differential prime ideals are finally generated. So stability in this case follows from quantifier elimination. The techniques introduced in the paper, perhaps more important than the final result. There's some beautiful work constructing a lot of, giving a very general construction of disintegrated strong minimal sets that live on algebraic curves of genus at least 2. And some results that have proved important in the work of Pillay and Noglu later on definability of orthogonality in families. Again, this works for orthogonalities to strong minimal sets except for the constants. And somehow this is something that came as a big surprise to me, because Tracy McGrail and I had noticed earlier that you couldn't do definability to the constants and had sort of ignored the problem completely after that. But that seems to be the only major problem. Okay. So on this slide, I'm going to give a very quick view of 3 other things. First one, is also extremely important. Udi gave constructed an algorithm for computing Galois groups of ordinary linear differential equations over Q. This is sort of extending things done by Singer and others. And there have been a few papers written by differential algebraists trying to come to terms with this and trying to make the algorithms more explicit and give certain bounds. Another result, and I won't go into this one carefully, is a result with Pillay, which is very much in the spirit of the Mardell-Lang type things, where you have an abelian variety, you have a subvariety with certain properties. I take a finitely generated group, and then I want to count the number of points on the subvariety that are in the group, but aren't algebraic points. And they showed that you can give double exponentially bounds in certain cases here. Again, there's been work recently of Omarli and Sanchez and Jim Freitag with various extensions of this result. And there's another paper of Tom Scanlon where the theorem is exactly the title. They showed that there was an old question of whether U rank and Morley rank were the same in differentially closed fields. They gave an example that it's not. The example uses some constructions of Boehm. It's fairly hard to see exactly where they get a difference in ranks. I think Freitag maybe has later examples showing that you can get a difference between somewhere at level 3 between Lescar and Morley rank. Okay. So having focused on the 2 things I like, focused on some of the things I like the most, I want to finish by giving what I'll call the lightning round, which is just sort of one slide with an overview of some of my other favorites. I mean, many of these things are things I've lectured on at various points in time, and are really outstanding work. The first, well, I'll state it more as a theme to begin with, and then I'll state some concrete works, is this idea of detecting the presence of algebraic structure. So looking at some various model theoretic properties, or looking at, say, the combinatorics of independence, and seeing that phenomena arise, seeing that when things arise, it's the avatar of algebraic structure. So the result I mentioned before, that non-trivial locally minimum modular sets arise from groups. The group configuration is certainly an amazingly surprising and beautiful version of this. And the weaker version of this, where you find a definable group from just a generically associative operation, which can be thought of as a generalization of We's theorem from algebraic geometry, are also great. And in the same spirit, the results with Zilber on finding a field in an amplitude-Zariski geometry, where one starts by assuming you have a field with the topologies with certain properties, and then argue that that's necessarily because you have a field and with slightly better properties that that's all you have. I haven't even mentioned, the model theory of difference fields is a major area, starting with Udi's work with Zoe Chatzirakis and Kobe Peterzil, and leading to his new proof of Manin and Mumford with better bounds than had been known at that time. We heard talks earlier this week about his results around the Frobenius automorphism, understanding that the fields from point 2 as being ultra products of algebraic closed fields and characteristic P with Frobenius, and the required extensions of the Lang-Vey bounds to include intersections with Frobenius is deep and beautiful work. The model theory of algebraically closed valued fields is certainly among my favorites, starting with the more model theoretic parts of it, the elimination of imaginaries, understanding what the stable part is and how types are dominant, which types are dominated by the stable parts. That was done with Deirdre Haskell and Dougal McPherson. Understanding the role of definable types, something which, although started in the definable types started in models of arithmetic, were sort of a key to understanding stability theory for a long time, but now have been, both in this work and later work in NIP, shown extremely important in unstable contexts, and leading to the model theoretic construction of a Berkovich space with Francois Lasserre, and then his work on approximate subgroups and connections to additive combinatorics. I mean, this is, and I could easily fill 3 more slides, but I think that's time to stop. So happy birthday, Udi. I hope everyone joins me here in wishing Udi a happy birthday. And hopefully we'll all have a chance to meet in person sometime soon. Thank you.
Yeah, if I may say, thanks very much, Dave. It was very moving for me to listen to this. And also, I have to say, I've been wanting to say to you also to what you said about Anand a few weeks ago. Really, not today, not just specifically about my results, but just the picture that I think you give of our field, the cohesiveness that it had and has, I hope, and well, I mean, some of the lines, some of the historical lines of the field, I found very moving. Thanks.
Thank you very much, Dave. Since this was the last talk of the day, I guess that people might be interested in maybe sharing their views about